In the first section, we looked at solving a system of linear equations by graphing. And we saw that, yeah, it's directly dependent upon how well we can graph those lines to find that point of intersection. We're going to look at two more ways of coming up with the exact same kind of answer, but without relying on the graph. We're going to do it algebraically. And the first of those methods is called substitution. Substitution is a method of solving the system of equations where we substitute an entire expression in place of a single variable in order to find the point of intersection. Again, I want to emphasize our goal here is to look at these two linear equations in these cases and find the point where they cross. We're looking for the coordinates written as a point. So how are we going to do that? Step number one, we are going to solve one of the equations for one of the variables. Remember, we're starting off with two of them, and I don't know about you guys, but I want to do this with the least amount of work I possibly can. So we'll talk about figuring out which equation to use so it'd be easier, and which of the variables to solve for so it would be easier. Step two, then, is we're going to substitute that expression that we just created in step one into the other equation. Remember, there are two of them, and we're going to solve that. That should give us one of our coordinates. But again, we're looking for both of them. So step three is we're going to take that value that we just found, go back to the equation that we used in step one, and solve it for the other coordinate. So then that'll lead us to step four. We're going to check both coordinates in both equations. It's going to be more substituting. Again, we're looking for the point of intersection, the point where these lines cross. But we're going to do it this time without having to draw the lines. We have to show that these coordinates are points on both of those lines. So let's take a look at the first one here. Now you'll notice y equals negative 3x plus 14. Well, okay, 14 spaces up. Good thing we're not graphing that one. And y equals x plus 2. They're already solved for y. If they're written in slope-intercept form, the equations are already solved for the y variable. So step one is taken care of. Step two, then, we're going to take one expression and we're going to substitute it into the other equation. So the way I'm looking at this is I know that y is equal to negative 3x plus 14 from my first equation. My second equation says y equals x plus 2. Well, I'm going to take out this y and I'm going to substitute that in its place. So instead of y equals x plus 2, this becomes negative 3x plus 14 equals x plus 2. Now, this is really, really important here. If you're doing the substitution the right way, you should come up with a brand new equation here that only has one variable. Now, sometimes you're going to substitute in the equation like this one is just going to be in terms of x. Sometimes it's just going to be in terms of y. But if you do the substitution and you get an equation that has both x and y, You didn't do it right. Let's go back and fix that. So now, again, we can see here, substitute the expression into the other equation. We can solve that because there's only one variable here. So if I add 3x to both sides, again, inverse operation, x plus 3x, that means I now have 4 of those. And if I'm going to move the variables over here to the right, I should subtract 2 and move the constants to the left. So 14 minus 2 will knock that down to 12. Divide by 4, and x equals 3. So that takes care of step 2. That gives me one of the coordinates of this point of intersection I'm looking for. So now I need to find the y coordinate. Fortunately for us, either one of those equations will work here with step 3. Y equals 3 plus 2, y equals 5. So I'm suggesting at this point, these two lines intersect at the point 3, 5. But now, step 4, I'm going to check. If I put 5 in place of y and 3 in place of x, doesn't make that first equation true. So I have 5 is equal to negative 3 times 3 is negative 9 plus 14. Well, negative 9 plus 14 is the same thing as 14 minus 9. 5 equals 5. That checks out. In the second equation, again, I'm saying the point of intersection is 3, 5. So 5 goes in place of y. 3 goes in place of x. And would you look at that? Both of them check out. I know that is the point of intersection. Now you look at practice problem number 2. Yeah, okay, things aren't quite as simple as the first one. So now let's talk about step 1. Go back here, solve one equation for one of the variables. Now we could, if we wanted to, we could take this first equation and put it in slope-intercept form. That would mean moving the x to the other side, and in this case, dividing by 6. Well, negative 1 doesn't divide evenly by 6, and 7 doesn't divide by 6, so we'd get fractions. Yay! No, I didn't hear anybody cheering. Take a look at the second equation, though. What jumps out at me is that has a coefficient of 1. It would be really easy, well, certainly easier than the first one, to take that second equation and solve it for y. So let's do that. I'm going to subtract 8x from both sides. So y equals negative 8x minus 7. And now I'm going to take this expression, negative 8x minus 7, and I'm going to substitute it into that first equation in place of the y, because it tells me this is what y is equal to. I'm going to take the y out and substitute that in its place. So this becomes 7x plus 6 times, I'm going to take out the y and substitute negative 8x minus 7 in its place, and everything else stays the same. Now again, a quick check. my equation here. I've got an x, and I've got an x, and I don't have any y's anymore. All right, so next thing I need to do here is the distribution. Get rid of that set of parentheses. So 6 times negative 8x will give me negative 48x. And then 6 times negative 7 will be minus 42. Again, everything else stays. Then we need to combine like terms. Well, here I've got both of the variables on the same side, so I don't have to change. All I have to do here is take 7 minus 48. That should give me negative 41x. Now I'll have to add 42 to both sides to move the constants over. So I'll have negative 41x is equal to, well, positive 41. Divide both sides by negative 1. I'm sorry, negative 41. Negative divided by negative is positive 1x. 41 divided by negative 41 is negative 1. So I'm saying these two cross at a point where the x is negative 1. Then I'm going to take this, and I have an equation ready to go here to tell me what y equals. I'm saying x is negative 1. So I'm going to substitute that in place of the x right there. So negative 8x becomes negative 8 times negative 1. That's positive 8. 8 minus 7 is 1. So I'm saying that the y coordinate is positive 1. And then, of course, I'm going to check. Get rid of all of this stuff from around my equations here so I can see them better. 7x plus 6y equals negative 1. So if I'm going to substitute what I think is the correct answer here, that means 7 times negative 1 plus 6 times positive 1 should equal negative 1. And sure enough, 7 times negative 1 is negative 7. 6 times 1 is 6. Negative 7 plus 6 is negative 1. And I'm going to check the other equation also. So 8 times negative 1 plus 1. 8 times negative 1 is negative 8. Negative 8 plus 1 is negative 7. It checks out. These two lines cross at the point negative 1, 1. So as we're looking at the equations they give us to do the substitution method, if like this one, and they put them both in slope-intercept form for us, well, y equals this and y equals that, you can set this equal to that. If they don't give you the equations in slope-intercept form, then what we're looking for is a term where the coefficient is 1. Something where it would be really easy to solve and get that one variable all by itself. All right. Hopefully that all makes sense. And when you come to class, we can get to work and see if we can find some intersecting points without having to graph them.